I will actually go through again this hybridization. Now, hybridization, okay, as you know, okay, is something when you have orbitals. If you have s orbitals, and then if you have p orbitals, when they join together, okay, you will have some kind of a modified orbital that looks like something like this, okay, when you join. So it means that this is a hybrid orbital. So this hybrid orbital contains both the property of s and p. Okay, and these hybrid orbitals, the way we draw is almost same for all the hybridization. So under hybridization, we have three types of hybridization. One is going to be Sp3, we have Sp2, and we also have Sp hybridization. For our syllabus, we will focus only on the hybridization for carbon atoms. Okay, so let's actually go on further. Okay, when you go on further, okay, here, okay, all this starts from carbon. Okay, all starts from carbon. So we know that the electronic configuration, okay, for carbon is going to be 1s2, 2s2, and 2p2. So if I just draw in terms of boxes, okay, for this, I will write down like this, okay. And then the electrons, if I put in the electron will be something like this, one and here. Now, what happens, okay, this one is called ground state. Okay, this is always a ground state. They are not ready for bonding or something like that. But okay, when they participate in bonding, okay, there is a new state that will actually emerge. Okay, that new state is called excited state. So they get excited for bonding. Okay, they get excited for bonding. So when we draw, okay, what happens is the electron, okay, from the 2s, okay, they will actually move towards 2p because it is from the same principal quantum shell. So the electrons will move, can actually move, okay, so they will become something like this. If I'm drawing over here, so if this one I put it in yellow color, okay, what happens is this electron, they come over here. Okay, this is excited state. So excited state is going to happen whenever they are preparing themselves for bonding. Now, it depends, okay, the mixing of orbitals. All these are orbitals. So you see orbital number 1, orbital number 2, orbital number 3, orbital number 4. Okay, so this one is called orbitals, and these orbitals can actually, okay, these orbitals, they can mix, okay, they can mix. So how they mix, okay, it depends, yeah. So depends on what you need, okay, depends on what you need. So in that case, okay, we will look at some examples. Okay, one of the example, okay, I'm going to actually select CH4 as one of the example. Now, if you look at CH4, okay, so let's actually look at carbon itself here. The carbon is being bonded to total of, okay, 1, 2, 3, 4. Okay, 4 hydrogen atoms. So there are 4 bonding that is involved, okay. So if I actually draw this in electron form, so it means that if let's say carbon is going to be 4 valence electron, they are going to be shared with uh, 4 more electrons from hydrogen. Okay, so we need to actually make sure that carbon, okay, under the excited state, okay, we need to actually make sure that they have enough space or enough orbital for those electrons to come in. So I need 4 space, okay, for those electrons from hydrogen to come in. So what I will do is I have to actually do a mixing of orbitals. Okay, if I just change it into green over here, so what happens is the one of the electron will come over here. One of the electron can come over here. One of the electron can come over here. One of the electron can come over here. Okay, it means that I am utilizing this 1s orbital, and I'm also utilizing 3p orbitals. Therefore, I can say that this particular carbon, the orbitals that is involving for the bonding, which is this one, these are the orbitals. The orbitals that are involved for bonding, they have actually changed into hybrid orbitals. And those hybrid orbitals are known as Sp3. Why they are Sp3? Because you choose 1s and 3p. Okay, so therefore they are going to be named as Sp3. And this Sp3, it means in total, okay, students get confused. Sp3 means how many orbitals in total? Yeah, of course, if you look at it in total, it's actually 1, 2, 3, 4. 4 orbitals. And you can see from the diagram, 1, 2, 3, 4. So if I represent this diagram in terms of a hybrid orbitals, how will it look like? This is going to be the hybrid orbital. So it will look like this. Carbon, okay, carbon, and then you have one hybrid orbital. You have the second hybrid orbital, third hybrid orbital, and the fourth hybrid orbital. And when you actually bond, okay, with the hydrogen is actually from H1, so it's 1s1. So it means the s orbital. S orbital is always going to be sphere. So there is nothing changed for the hydrogen. So the hydrogen, they will actually form something like this. So this one is from hydrogen. Of course, okay, the electrons will come under the part that they are overlapping over here. So I will actually highlight the overlapping part as here. There are 4 overlapping parts, okay. These 4 overlapping parts, they are actually known as, okay, ends on overlap. So ends on overlap, okay, they are also named as sigma bond. Okay, sigma bond. So they actually given with this symbol sigma. And if I just look at CH4, how many sigma bond? Okay, there are total of 4 sigma bonds over here. Okay, 4 sigma bonds. So let's actually look at other examples. Okay, so we have done, okay, with this Sp3. Okay, let's actually have a look at Sp2. Now for Sp2, okay, I'm going to actually use this example. Now, why I don't actually draw another hydrogen below? Okay, this one in IGCSE you should know. All carbon atoms, they have 4 bonding. Okay, so if you have 4 bonding, okay, means 1, 2, 3, 4. Okay, you don't have another hydrogen over there. All carbon have 4 bonding, so 4. Okay, there is no extra 1 hydrogen. Now, what I want you to actually do when it comes to A level is you forget the fact, okay, it's going to be only for bonding. You start to actually ignore the double bond first, okay, ignore the double bond. So it means that if I just look at carbon, if I ask how many bonds surrounding carbon, okay, there are 1, 2, and 3. Okay, let's actually focus on this. Directly, physically, each carbon is being bonded to 3 atoms. What are those atoms? 2 atoms of hydrogen and 1 atom of carbon. Okay, so 3. So we know that, okay, earlier when we actually did the ground state and excited state, I will actually take this this part here.
Sir, may go toilet, sir.
Yeah. So if I put it here, it's the same, okay? So you have the same situation here, but the difference is, okay, you have excited state. Excited state. Now the excited state is still the same, okay? It's still the same. We just put, okay, still they need to be bonded to 3. Okay, so if you just focus on the ground state, they don't have enough place for the 3 bonding. You can see that only 1 and 2 only. Okay, so what you need to do, you get excited first. Carbon gets excited. So 1, 2, 3, 4. Okay, once they get excited, okay, not all of the orbitals will be used for bonding. Okay, why not all of them will be used for the bonding? You can see they need only 1, 2, 3. So if you need only 3, okay, you need, okay, the one of the electron from the hydrogen, they will come over here. Another one more electron from this hydrogen, they will come over here. One more electron from carbon, they will come over here. So it means how many orbitals that are involved for hybrid, or how many of them have to readjust themselves or mix. Okay, it means this orbital, and this orbital. So we call this, okay, we know this is S, we know this is P, we know that this is P. So this is going to be Sp2 hybridization. Now, under Sp2 hybridization, what happens, okay, you are going to get 3 new orbitals. So 1, 2, 3. So I will actually put, okay, 3 new orbitals like this, hybrid orbitals. But do not forget, there is one orbital which is over here that do not get hybridized. So it means they are still going to be in this form. Okay, they're still in this form. Now, what is going to happen? Okay, let's actually look at what is going to happen. Under this structure, if I represent this, okay, do remember we are just focusing on the 3 bonding. Okay, the 3 bonding over here, hydrogen and hydrogen. So if I put carbon, and then I want to actually show 3 bonding, so I will look like something like this: 1, 2, 3. Okay, that's for this carbon. Okay, let's actually focus for this carbon. Okay, so let's say I'm going to actually copy this diagram. I'm going to paste it here. Now, do remember, okay, do remember that this carbon and this carbon, they join together. So let's actually bring them closer. They join together. Okay, they join together. And then I will use the hydrogen. Yeah, now hydrogen is to I'm going to draw something like this: hydrogen, 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 hydrogen. And we can see from here there are some overlaps. Okay, this is one of the overlap, another one overlap, another overlap, another overlap, another overlap. And all these overlap that I mentioned just now, these 5 overlaps, they are sigma bond. Okay, so 5 sigma bond because they are ends-on overlap. Okay, I hope until now is clear. Now let's actually include the part that will be confusing. Okay, what is the part that is going to be confusing? Just imagine we have done this, this, and this, and each carbon still have this one. So how do I represent this? Okay, so let's say I'm going to actually use a different color, red color, and let's say I'm going to actually represent them in a special way so that all of us can see. So let's say I'm just going to actually put a dotted line here, and then I'm going to also put a dotted line here. Now, I will draw a bit bigger so that we can see the overlap. Okay, so it's p orbital, yeah. So I'll draw a bit bigger. Okay, and then I'm going to use different colors so that we can actually see more clearly. There's another one here. I will draw a little bit bigger, something like this. Now, what you can see, or what you're supposed to see, okay, I will highlight in yellow. There's an overlap here, and also there is an overlap here. Okay, if I just make it a bit more like we can see, okay, imagine this one, okay, this one from each carbon. So what I did was one is in purple. So let's say I draw in purple and one is in red color. So if I draw in red color, it will look like this. So it means there is an overlap up and down. This kind of overlap, okay, they are called as sideways overlap. And do remember, okay, do remember, there's one electron, they are going to be overlapped with another one more electron from carbon. It means this is going to be filled by another one more electron from the carbon that has the, like, just imagine this is one set, okay, excited state. And there is another set for another carbon, and that electron and this electron, they will join together. It means one electron from here and another electron from here. They will actually move together. Okay, so when they move together, because it's actually sideways overlap, they will actually form some sort of an electron cloud, up and down. Okay, if you have a molecule, carbon, okay, and then we have another carbon, and you have H, 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 it means this, okay, this part, they will actually circle around the carbon. Even though it looks like a up and down, like burger, yeah, being the top part and lower part, we actually put them, okay, as one line only when we represent. So that one line that we put over there, that represents the sideways overlap. Now those sideways overlap, okay, is actually called, okay, both of them, okay, both of them is considered one. So it is called pi bond. Okay, pi bond. So it means now, okay, this one, okay, and this one, they are considered to be pi bond. And why they have actually some kind of ring on top of that, it means that those electrons, they are free to move up and down. And the term that we use when they are free to move, the term that we use is delocalized. And we have learned this term delocalized under metallic bonding. Okay, do remember pi bonding, you also have delocalized electrons. Okay, they do circle around. Okay, but here you see for normal cases, they don't actually get delocalized. They are only around here. They are only around here. So they don't get delocalized. But for this, okay, it means when you have pi bond, it means electrons, they are going to get delocalized up and down. Now, when you have something up and down, just imagine like this. Okay, this one is very important. If you have a friend and you are actually holding hands, okay, so what happens is you can actually do a flip, okay, or you can actually do a somersault or something. You can actually have a situation where this guy can still hold hands with you like this. Okay, it means that can still happen. Okay, that can still happen. But now imagine, okay, imagine I am actually putting something over here. I'm going to put a rope over here. And I'm going to put another rope over here. Okay, can you actually achieve this structure? I think both of you will die, right? Okay, yeah, eventually you will twist. Okay, so what happens over here is it's not possible. It means the movement is being restricted. Imagine these two ropes are actually the pi bonds. Okay, pi bond restricts rotation. Pi bond restricts rotation. It means that, okay, it means that if I have CH, Cl, and then I have another H, Cl, and I put H over here, it means that if I have another situation and I put CC, H, and I put the Cl to here, and then I have H, Cl, it means, okay, it means this and this are the same. Why? They can rotate. They can rotate, free to rotate. It means the Cl can come over here, Cl can come over here, it's still the same. But if I have C double bond C, the one that you have learned under hydrocarbon, if I have Cl here, H over here, H over here, and if I have C double bond C and I have H, Cl, Cl, this one we will learn again, yeah? But again, this is actually cis and this is trans. They say that this is cis isomer and this is trans isomer, geometrical isomer. And they say that this is different. Why they are different? Because there is no way that this Cl can come over here, because the pi bond will restrict the movement. It means if this is, if let's say this is Gopi, okay, this is Gopi, and this is going to be Miss Pugan, then it's totally different, even though it looks the same. Okay, because it's, you cannot actually, or you cannot say that this is Gopi part 1 and this is Gopi part 2. You cannot say that, even though they look identical. Okay, because they are totally different, because in nature, this thing and this thing should not actually occur at the same way, because the restriction that is being posed by the pi bond. I hope you understand this part. Okay, so that's why you have a different something called isomerism. Okay, that one we will learn later. So let's actually focus on the today's lesson again. Okay, so I have done, okay, related to sideways overlap involving, okay, Sp2. Okay, so this one is Sp2. Done. Let's actually look into Sp. Yeah. Now for Sp, the same thing. I will actually try to bring the ground state again. Okay, when I have this ground state again, and let's say the example that I'm going to look is C triple bond C. So you have H and H. Okay, when you have this situation, and I told you, if you look at that structure, just focus carbon is bonded to one hydrogen and also bonded to one carbon. Okay, ignore these two. Okay, so it means there are two bonding happening. So when you have two bonding that is happening, okay, when you have two bonding happening, it means you need to still rearrange, okay, still rearrange, but you still need to get ready. You still need to actually go into excited state, even though you are still ready over here. Okay, it's still not enough. There is should be a mixing of orbitals should be happening. So what happens again? The same, one electron here, and you have, okay, 3 electrons there. But since I just need 1 and 2, okay, it means that I will need the 1 electron from hydrogen will come here, and 1 electron from carbon will come over here. It means that I am only going to need Sp. So I need only Sp hybridization. So Sp hybridization got how many orbitals? 1 orbital, 2 orbitals. So Sp orbitals, you have 2 Sp orbitals. Okay, do remember when I draw just now, okay, each of them, okay, each of them here, I have this is Sp2, 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 and this is P. So if you have this, okay, it means that you have 4, okay, which is 1, 2, 3, 4, yeah. So you have 4, and all of them are called Sp3 orbitals. So now I am going to have 2 Sp orbitals, and the rest, they do not get hybridized. So I'm going to have something like this, P and P. So what's going to happen, okay, when I have this kind of situation? So you will have, okay, you will have something like this, carbon. So I'm going to have something like this, something like this. And you have 2 carbon, okay, you have 2 carbon. So let's actually select this. So I'm going to paste it over here. And do remember the carbon and carbon, they overlap. Okay. So when they overlap, so I bring over here, they overlap. And then I have hydrogen and hydrogen left and right. So I draw hydrogen and hydrogen, hydrogen, hydrogen. So here, if I actually put it in blue, this is sideways, ends on overlap. So you have total of 3 sigma bond, 3 sigma bonds. Okay, and then do not forget, okay, that we also have, okay, we also have this and this. Okay, now to show this, it's going to be quite difficult, so let me actually redraw this again, see whether I can. Maybe I'll just put it a little bit nearer, a little bit nearer. So hydrogen, hydrogen, hydrogen. So still, okay, still sigma bond, sigma bond, sigma bond. Now, do remember the carbon, okay, the carbon, each carbon has 2 p orbitals. So let's say one of it, I just want to actually show like this. Okay, and I will use blue pen, okay, you take note, P. And if I highlight the overlap, sideways overlap, okay, do remember this one is done. Okay, and we also have, okay, another one. Okay, things will get messy now. So just take note. I'll use this color. Okay, so you still have another one. So let's say I try to actually draw somewhere nearer so that I can really show. Like this. Like this. And that will actually give me another pi bond. Can you see? And I told you it's going to get messy. But it means like this. Okay, it means that the 2 p orbitals, okay, one of it, okay, they will actually overlap with another carbon like this. And then there is another p that will overlap at different direction, something like this. So there are 2 pi bonds. Okay, there are 2 pi bonds. Okay, so that's why, okay, you have the additional 2 lines over there. Okay, it means that, okay, it means that if I actually want to find out how many sigma bond and how many pi bond, okay, 1 sigma, another 1 sigma, another 1 sigma, and these 2 will become 2 pi bond. Okay, so if I actually try to recall whatever things that I actually taught you, okay, if you have CH4, okay, CH4, you need, the carbon needs 4 orbitals, okay, for bonding. If you need 4 orbitals, the carbon have to be hybridized to give you 4 orbitals. Therefore, I need Sp3 hybridization. Okay, just remember Sp3 means 1s and 3p. So you join them together, you have 4 orbitals. So 4 orbitals, 1, 2, 3, 4, 4 orbitals. Sp3 hybridized. And if I ask you how many sigma bonds are there, quite simple, 4 sigma bonds. Okay, 4 sigma bonds. Let's actually look at this example, C double bond C. So if I ask you, what is the type of hybridization? Quite simple, just look at, okay, the how many bonds you have, 1, 2, 3. Ignore the 1 bond over there, 1, 2, 3. Directly bonded to the elements, okay, 3. So you need 3 orbitals. So in order to get 3 orbitals, you need Sp2. Why Sp2? 1s and another 2p. So total you have 3 orbitals. So when you have that, how many sigma bonds that we are having? You will have 1, 2, 3, 4, 5. 5 sigma bond. And how many pi bonds that we are going to have? Only 1 pi bond. Okay, so let's actually go for another example. C triple bond C. So you have H and H. How to identify the type of hybridization? Again, look at this one bond and another bond. Okay, they are bonded to 2. So we need 2 orbitals. Okay, so therefore we need sp hybridization. Why sp? One s and another p. So total 2 orbitals. Okay, so the rest, okay, this one is going to be sigma, 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 3 sigma bond for this molecule, and there are total of 2 pi bond over here. Okay, 2 pi bond. Okay, now if I actually ask some additional questions, okay, additional questions. For example, okay, if I ask you, now, is the sigma bond over here is the same as the sigma bond over here? Okay, there is a slight difference. Okay, what is the difference? One is carbon with hydrogen. Another one is carbon with carbon. Now, if they ask you what type of orbitals that are involved for this sigma bond, what type of orbitals? So you take a look at the diagram. Now, this is s orbital. Okay, this is s orbital. And this is going to be hybrid orbital. So if I actually want to actually find out what type of overlap, this is the overlap between s with the carbon, which is 1, 2, 3. 1, 2, 3 is sp2. So it means that it's the overlap between s and sp2. Okay, it's the overlap between S, which is this one, S, and sp2. Quite simple. Okay, this one is a different example. Yeah, so S and sp2. And if I ask you what type of overlap for this sigma bond over here, this one is actually between the the hybrid with another hybrid. So it's actually this sigma bond belongs for sp2 and sp2. Okay, later I have some questions, okay, that I took from the past year paper. Okay, we can actually see that, okay, it's actually nothing to be confused about. Okay, if it is like this, okay, if I give you one example, yeah, if I have
Sir,
C with
sir.
C, yeah,
Cannot set he got disconnected, sir. He can't go back in.
again,
Cannot say he got disconnected. He can't go back in because he locked the room.
oh, who
Cannot.
can, okay, ask him to join again. Okay, so when you have this, okay, let's say I'm going to actually still do something like this, H, H, H. Okay, you have a combination, for example. Okay, if I ask you what type of sigma bond is here, what type of sigma bond is here, and what type of sigma bond is here, okay, so you should be able to give me answer. Okay, what orbital with what orbital? Okay, for example, okay, the s orbital, it means each of these carbon, they are going to undergo hybridization. Okay, they will undergo hybridization. If you look at this carbon, they will undergo, because they need 1, 2, 3, 4. Okay, if they need 4, they will undergo sp3 hybridization. Okay, sp3 hybridization. So for this, what type of overlap that is happening for the sigma? It is between, okay, the hydrogen and the hybrid orbitals of that carbon. So the hydrogen, okay, is 1s1. So it means the hydrogen will be the circle. Okay, and then this one, each of them, they will have some kind of a overlap like this. Okay, it means it's this orbital and this orbital. So what is the orbitals that are involved? It's s orbital with sp3. Okay, so if I go into this example now, okay, I know that this is 1, 2, 3, 4. Okay, this for this carbon is sp3 orbital. Okay, but this carbon is slightly different. Why? 1, 2, 3. So they will get sp2 hybridized. So the sigma bond is between sp3 and sp2. Okay, sp3 and sp2. Let's look at the sigma bond over here. For this carbon, okay, 1, 2, 3, so it's sp2. How about this carbon? So 1, 2, 3. So still sp2. So they have asked this kind of questions before. Okay, what kind of orbitals that are overlapping? Now, there is another question. Let's actually look at this. This is the very easy one. This pi bond, okay, this pi bond, what kind of orbital overlap? Very simple. Always pi bond is always going to be P and P. P and P. Okay, it means the one that is actually do not get hybridized. Okay, so pi bond, when they ask you what type of overlap, is always P and P. Okay,